So in this lesson, we're going to be referring to the interior and exterior angles for 4.03 exit ticket. Starting with a little bit of a warm-up, we recall that to determine the slope between two ordered pairs, we have x1, y1, x2, y2. So for slope, we have negative 2 minus 5, all divided by 5 minus negative 2. Here we have negative 7 divided by 5 minus negative 2 is positive 7. So we get a slope of negative 1. So we should get a slope of negative 1 for our warm-up here today. Okay, so our objectives will be to classify polygons, to classify a polygon as concave or convex, determine the sum of the interior angles of a polygon, and determine the sum of the exterior angles of a polygon. To achieve that, we're going to talk about polygons and the naming conventions and practice problems related to that, as well as whether they're concave and convex. We're going to talk about interior exterior angles and the practice problems for those, and then I'll illustrate a few of the slides that I would refer back to help you most specifically with the exit ticket. I'll actually be referencing those prior to going to the exit ticket itself. So let's talk about naming polygons. So a polygon is a closed figure formed by 3 or more line segments in a plane, such that each line segment intersects exactly 2 other line segments and their endpoints only. Let's unpack what that just said. Okay? So if you take a look at the examples of the polygons, firstly, we know that they're going to be closed. And when we say we know they're going to be closed, that's an extremely important statement to make. They have to have at least 3 or more line segments in a plane, and they have to be closed. Each and every one of these has more than 3 line segments. It has to have at least 3, which means it has to be a bare minimum a triangle. Okay, so let's highlight that particular statement there because I want to single that out. Okay, so I've gone ahead and I've highlighted that part of it right there, right? And then the other part I want to highlight as well is the line segments form the sides of a polygon. That's what those edges are. Sometimes we refer to them as edges. And then a point is where the sides intersect at a vertex, which, by the way, that's actually what this statement here is saying. The segments intersect at exactly 2 other line segments at their endpoints only. But it just so happens to be that the endpoints of these line segments are the vertices of the polygon. And so you can see that here and here and here as an example. Those are the vertices of the polygon. They happen to be the endpoints of the segments. And when 2 segments intersect each other, as they do in this case here, they're only intersecting at a vertex, nowhere else. Okay, so you see some examples that are polygons and other examples that are not. Like the circle is not a polygon, and the middle two, or the middle and the last example, are also not because they violate some of those conditions that I highlighted. It is also the case that you can have, there's no upper limit on the number of sides a polygon can actually have. So let's go ahead and take a look at these, and we're going to classify these multiple times over. But the first thing we want to do is just determine whether they're a polygon or not. So in this particular case, this one has an opening right here, which means it's not closed. So this is not a polygon because it has that gap right there. But if you look at the other 4, regardless of whether they're regular or irregular shapes, you can see that they are closed forms, that you can see the vertices of the respective figure or figures. Some of them might be recognizable shapes to you, like perhaps the trapezoid or the octagon on the far right there, if you already know the name of that, the stop sign that is. Those are the vertices of the figure. And it's closed because the segments only intersect each other at those vertices, and there's never an opening anywhere around the entirety of the figure. So another way to think about that is if I were to start, let's say I were to take a point and I was going to start here and trace along the figure's edges. The problem is that it's not closed because, and I didn't mean to do that, so I apologize, I can't achieve getting to the original point without lifting up my pen and actually jumping across, right? So that's another way of seeing why it's not going to be closed. So all of the others here are actually polygons. These are all polygons and are examples of polygons. Now the word poly means many, and gon technically doesn't mean side. Usually it means corner or angle, but it actually still represents the same number of sides because the same angles that we have in there is equal to the same number of sides. So you can still refer to it as a many-sided figure, but remember that a triangle is technically a polygon as well as a quadrilateral. Okay, it doesn't necessarily mean that a three-sided polygon is not that many. All of those are polygons. Speaking of that, we want to go through the naming conventions. So when we name polygons, we usually refer to the number of sides, but also technically you can refer to the number of angles as well, or the number of vertices, because that's going to equal the same number. And so I like to say that mathematicians tend to get lazy because after 13 typically, we don't typically refer to it as a specific name, but rather just n-gon. So like 13 gon, 14 gon, all the way up to 27 gon and beyond that. And you can keep going. As far as the 11-sided polygon, it's just not as popular as well-known of a name. Technically, we tend to refer to it as a henogon, or a hendodecagon, or hendecagon, I should say, rather. So it's a hendecagon. If you wanted to name it, there is a name for it, and there is a name for 13, 14, 15-sided polygons. It's just the names start to get really unruly and long, and we tend not to want to name them that way, so we just get a little lazy and start calling them 13 gon, 14 gon, and so on. So for example, a henogon actually is on the screen right now. The lightning bolt and the lightning bolts above are an example of a henogon because they have 11 edges or sides. So that's actually an interesting little fact there. If you look at the screen and you count those sides, you actually get 11. So having said that, we're going to use those names. Some of the more common ones are pentagon and hexagon, heptagon, octagon, nonagon, decagon. Heptagon and nonagon aren't as well known, but certainly penta, hexa, and octa, a lot of times people remember those very well. So we want to make sure to reference this, especially because you need to use the names of the polygons in order to determine the number of sides. So returning to the original diagram of those particular problems that we have, we can now go ahead and name the figures, right? So remember we said that this is not a polygon, so of course we're not going to actually classify that. But remember how I was going around and describing the vertices, right? So you can see that there's 6 of those, right? You can also label the number of sides that you have, right? So you have 1, 2, 3, 4, 5, 6 sides. So we know that that's what we refer to as a hexagon. And I'm just naming this figure by the number of sides. I know it is likely a quadrilateral, or a trapezoid rather, but I just gave the answer as well, which is that it is indeed a quadrilateral, which refers to how many sides the figure has as opposed to what type of relationship its lines are to each other. And so the last two here, if you go around and you count all the vertices or all the sides, you actually count up 8 for both of these. So these are actually both octagons. It's just the one on the left is what we might refer to as an irregular octagon because it's an odd shape for an octagon. So that's a way of classifying those. And then another modifier or adjective we can use to describe these would be concave or convex. Now, I have my own way of explaining why this works the way that it does, but there's several different illustrations that you can use to refer to why is it that a convex polygon is described as it is in concave. So I'm going to start with the concave down at the bottom first because I really want to highlight this little fact. If you look at the word concave, it actually has in the suffix of the word cave, right? So you have con and then you have cave. So if you look at the images to the far right here, you can see that a lot of them actually have this little cavity area here. So here's a little cavity right here. Here's some cavities right here. I guess in some ways the cavities you get on your teeth would represent a cavity as well. Anytime you have cavities like that, you have some caving in, right? They're caving in on themselves there. What are the segments representing? Well, if you have 2 points interior in the figure and you draw a segment that connects them, and any part of that segment is outside of the figure, that is an example of a concave polygon. However, another way to think about it is if you look at the vertices, many of the vertices are pointing outwards. However, if you look at the one vertex here, it's actually pointing inwards. Anytime you have a vertex that's pointing inwards, that's also a concave polygon as well. You've got a few of them right here, actually. Or you have a few of them right here. Same number of cavities in the figure is the same number of vertices that are pointing inward as well. So that's just an illustration or an example of that, as opposed to these that are convex. If it's not concave, it's convex. Nowhere inside of this or even on it, if I put 2 points, if I connect them, will the segment connecting them be outside of the figure. And again, another way to think about it is the vertices are all pointing outwards. Okay, so if you look at all these convex polygons, their vertices are pointing outwards completely every single time, no matter where I'm looking. That is an example of a pair of polygons that are convex as opposed to being concave. Now, the reason why you're seeing that is because we want you to know the difference, because there are certain rules with the sum of the interior angles and exterior angles that apply specifically to convex polygons, and we want to make sure you understand what that adjective actually means. So returning back again to my original figure here, now I can actually be even more specific than before, but I'm just going to name them in terms of concave and convex now. So I know that, again, that's not a polygon, and I can see here that there is a subtle concavity on the sides, and then there's a more prominent one below. So you can kind of see there's if I use the example for interior points, there is a segment portion or a piece of the segment outside of the figure, like there, for example, as well as the fact that this vertex is pointing inward, as are these. So that tells me that that is going to be concave because it's caving in. This is convex right here. This is convex right here because those are pointing out, meaning the interior is going to be entirely containable for those segments that we talked about. If you draw 2 points interior to the figure, the segment connecting them will always be contained inside. That's what makes these convex. This one is a very abrupt and very clear concave figure. In fact, it's so clear there's a very large cavity for this particular octagon right here. And so that makes that a concave octagon. So it tells you a little bit about the structure, about the figure itself when you're trying to identify what type it actually is. Which leads me now into interior and exterior angles. So obviously we know that interior angles means inside of the figure, and we have an example of that with, if you look at the odd numbers, right? So for the interior angles, we have all of the odd numbers, and then of course the exterior angles are going to be the even numbers in this case. So we see that we have 2, 4, 6, 8, 10, and 12 as exterior. That's a hexagon as an example. And so polygons have interior and exterior angles. So what I would ask you to do is maybe pause briefly and just identify what angles 1, 2, and 3 actually are supposed to be. Are they supposed to be interior or exterior? Hopefully you said interior angles. Of course, they're all contained within the triangle itself, so they are interior angles in this particular case. Angle 4 is an exterior angle. Now, I'm going to remind you here kind of an important little rule here. The sum of all the angles inside of a triangle is technically 180 degrees. Normally, just pointing this out, we would usually write it as measure of angle 1 plus measure of angle 2 plus the measure of angle 3 is going to equal 180 degrees. And that's important because you can actually work with that to determine why the sum of all the angles inside of any polygon is equal to this particular formula here. This is our formula, which we refer to as I because it represents the letter representing interior angles. For a convex polygon, okay, specifically convex. So I want to explain kind of what they're talking about here. If I were to draw a quadrilateral, and let's just go ahead and make it some parallelogram styled quadrilateral like this, because it could be any quadrilateral. And I start at a vertex, and I say, this is my reference vertex. I want to draw, or I want to make sure that all other vertices, and let's use a lighter blue color, I want all other vertices to be connected to that reference vertex. Two of them already are, but the one that's not is this one that's across the diagonal. So let's go ahead and connect it. And when I do connect that, what happens is I split up this quadrilateral into two triangles. Now, I mentioned earlier the sum of all the angles in a single triangle is equal to 180 degrees. So when you add up 180 twice, or when you multiply 180 rather by 2, you get 360 degrees. That's what this formula over here is actually referring to. In other words, what I'm saying is that this right here represents the number of triangles in the figure, in the polygon. And there will be, in this case, always 2 fewer triangles than there are sides in that figure. So the sum of all the angles, interior angles of a convex polygon, is a multiple of 180 degrees. So that same number right there is represented right here. That's how many triangles you see right there in my diagram. And so the sum of all the angles in a quadrilateral with just 4 sides is going to be 360. To use the formula, you're just substituting the number of sides n, which is right there, for where n is located in the equation. You're simplifying, and then you're just multiplying that number by 180. This is why it's important that you have a minimum of 3 sides, right? Because you can even use the formula with a triangle. The sum of all the angles in a triangle is 180 times 3 sides minus 2, which is 180 times 1, which is 180. If you have anything less than 3 sides, you're going to get either 0, no angle sum, or you get a negative value, which doesn't make any sense. So having said that, I want you to find the sum of all the angles interior, that is, in this particular convex octagon. So you should have arrived at 1080 degrees. Again, you take 180, you have 8 sides, and you're subtracting 2, so you get 180, again, times 6, and 180 times 6 is 1080 degrees. So that is going to represent an octagon. This would have been a heptagon, which is a 7-sided polygon. This right here is our octagon, and this is a nonagon. Okay, and this total sum of their degrees. You can also use a reference angle or a vertex to see the illustration. So remember, you're trying to connect all the other vertices to that. So for example, if I connect this one to that because it's not currently connected, I connect this one to that, it's not currently connected, I connect this one to that, it's not currently connected, and so on. I have one more here. Now I can count up how many triangles I have. 1, 2, 3, 4, 5, and 6. That same number of triangles matches this number right here. So that's kind of a visual way of understanding what that formula there at the top is actually saying and actually doing. So now we get to a problem that I marked down as an exit ticket helper. That just means that this slide would be very helpful for one of your exit ticket questions. And what we're targeting here is to find this value of x, and the first thing we want to do is identify how many sides we have. Well, in this case, we have 1, 2, 3, 4, 5. So we have 5 total sides. That's important because for number 1 here, we're going to go ahead and identify what the total sum is going to be. First, that means just calculating I. So since n is 5, I'm going to go ahead and input that. So here I get 180 times 3, which is 540 degrees. Number 2, I'm going to go ahead and I'm going to solve for x. That's the next step, right? That's the variable I'm trying to find because that's missing. So in order to solve for x, we're going to take all of the angles. We have 94, we have x, we have 158, we have 94, there's another 94, and then 102, and that is going to equal 540. So all of the numerical values add up to 448. We have that x there, and we have 540. So now we can subtract the 448 from the 540, and we can solve then for the value of x. So here we get 92 degrees for our value of x. So that would be my tip for that, for an exit ticket question. This is going to be very helpful for you in how to solve or set up that problem. And likewise, this example will also do the same thing, right? So we go around, we say, okay, 1, 2, 3, 4, so there's 4 sides. And then remember that you're finding x. So number 1, you want to figure out what the total sum is. So 180 times 4 minus 2, we just did this. 180 times 2, that's 360 degrees. Number 2, we're going to go ahead and figure out what total sum is going to be. So in that case, we're going to solve for x. Remember, that's the step if I don't want to describe it. So to solve for x, we have 47 plus 73 plus 113 plus x is equal to 360. And remember that what we're going to do is combine all of these together because they're like terms since they're just constants. So we get 233 plus the remaining variable x equal to 360. We're going to go ahead and subtract that from both sides, and then that gets x by itself, which is ultimately what we wanted. So we get 127 degrees for the value of x. There we go. Again, exit ticket helper right there, because that might be helpful for your exit ticket. So we get to the final part now, which is of course the sum of the exterior angles. And this is a reference page, of course, as you can see, but it is very helpful because it can remind you of a very, very strong and simple rule. The sum of all the measures of exterior angles in a convex polygon will always be 360 no matter how many sides it has, no matter what type of convex polygon it is. Okay, so just remember that exterior means outside. Like rather than inside, it's outside, right? So look at them adding all of the even angles up here because those are the exterior angles. So what did that rule actually say? Well, remember the sum of the measures of the exterior angles of any convex polygon is always going to be 360 every single time. Remember, it said exterior, not interior. So another exit ticket helper. This one will help on your exit ticket as well. Here we're finding the value of the variable x, and we notice that we have x missing, and it looks like we have this angle missing, but actually because this is a 90-degree angle, this is also going to be 90 degrees as well, so don't forget that. So we can go ahead and add all of these angles up, 70 plus 80 plus 50 plus the 90 plus x is equal to 360. And of course, as you know, these are going to end up being all of the terms we can add together. So here we end up with 290 plus x equal to 360. And then I'm just going to go ahead and subtract the 290 from the 360. So I end up with a nice 70-degree angle there for x. So that's how I use the exterior angle theorem, which is what that's referring to figure out that value of that missing variable there. So in the final example here, another exit ticket helper. This is the final exit ticket helper. This one wants us to determine what is the measure of each exterior angle if the regular polygon has 20 sides. This is very easy. To determine this particular statement right here, in fact, I'm going to see if I can copy it. Measure of each exterior angle. I'm just going to copy that part of it. Let's see if I can copy and then paste. And then I'm going to decrease the size of that. Okay, the measure of each exterior angle is going to and this is supposed to be in a regular polygon. It's very important that you understand it has to be a regular polygon. Okay, so regular polygon means all the sides are equal to each other. It actually has to say that in order for you to do this. Okay, it also means that all the exterior angles will be the same. So all exterior angles are the same. And technically all the interior angles are the same. That's also true as well. So here all we do is take 360 and we divide by the number of sides. So that would be 360 divided by n. So in our case, 360 divided by 20 is going to equal 18. So that means each exterior angle measure is going to be an 18-degree angle if it is a 20-sided polygon. Okay, that is the illustration of how to calculate that specifically. So I utilized this information here to help me answer that question, and it asked for each exterior angle of a regular polygon. You can only do that on a regular polygon, as is the case here. So here's your exit ticket. I already referenced all of the slides that you would need to assist you on each of these questions. And so you can make sure to get that done. Please refer back to the video and to those slides for each of the particular questions that can be helpful to you. One where you have exterior angles provided, so you're finding x. One where they're asking for the number or the measure of each exterior, which is just like the last example. And then the one on the right is referring to interior angles as a tip. So again, refer back to the slides in the video I discussed that can help you on those questions, and then that is going to represent lesson 4.03 over interior and exterior angles.